Welcome to Lesson 6D, Vorticity and Heat Flux Analogy. In this lesson, we'll introduce an analogy between heat flux and vorticity flux at a wall. This will hopefully help us understand how vorticity is produced at a wall. For simplicity in this analogy, we'll consider only 2D incompressible Newtonian flow in the xy or x1, x2 plane. We'll consider heat flux first since you're more familiar with that. Suppose our wall is parallel to the x-axis, and qy is the y component of the heat flux vector, which is the rate of heat transfer per unit area to the fluid. Recall Fourier's law of conduction, that this heat flux qy is minus k del T del y, where k is the thermal conductivity. Right next to the wall, qy wall, is shown with this subscript wall. Fourier's law states that heat flux at the wall, this term, is directly proportional to the negative of the temperature gradient at the wall. Since all we see is the derivative of temperature, the actual value of T is not important, just its slope. There are three cases of interest here. Number one, when the slope del T del y at the wall is negative, then by our sign convention, qy is positive, and heat flows from the wall to the fluid. This is the case with a hot wall and a cold fluid. Energy, or heat, is being added to the fluid, so we can think of this as a source of internal energy, or temperature, at the wall, or a production of internal energy at the wall. Case 2 is the opposite when the slope at the wall is positive, as illustrated here. In that case, qy is negative. In this case, we have a cold wall and a hot fluid, so heat flows from the fluid to the wall, or energy is being removed from the fluid. As I illustrate here, we can think of this as a loss of internal energy or temperature at the wall. You can also think of it as a production of negative internal energy at the wall. Finally, case 3 is when there is no slope, as I illustrate here. This would be the case of a perfectly insulated wall, so there is no heat transfer. No heat flows from the wall to the fluid or from the fluid to the wall. In other words, energy is neither added to nor removed from the fluid. There's no production of internal energy. There is still a redistribution of internal energy, but that's energy that already exists in the fluid. I comment that viscous dissipation leads to some internal energy production within the fluid. So our analogy is not perfect, but we're talking about heat flux right at the wall. The bottom line is that there's no heat flux unless del T del y at the wall is not zero. This should be familiar to you from your study of heat transfer. Now let's make our analogy with vorticity flux. Consider the same wall, and we'll let omega z be the z component of the vorticity vector. In our analogy, vorticity is analogous to temperature, or internal energy, and vorticity flux is analogous to heat flux. Again, we have three cases of interest, just as in the heat flux case. And I pretty much copied and pasted these diagrams, just changing the labels. The first one is for a negative slope of vorticity at the wall, as shown here. The vorticity flux is positive. In other words, there's a flux of positive vorticity from the wall to the fluid. Vorticity is being added to the fluid. You can think of this as a production of positive vorticity at the wall. Case 2 is the opposite, where the slope at the wall is greater than zero, and instead of positive vorticity flux, we have negative vorticity flux, or a flux of negative vorticity from the wall to the fluid, as sketched here. Instead of adding vorticity, vorticity is being removed from the fluid, so this is production of negative vorticity at the wall. Finally, when the slope at the wall is zero, it's analogous to our insulated wall case for heat flux, and there is no vorticity flux at the wall. Vorticity is neither added to nor removed from the fluid. There is no production of vorticity at the wall. If vorticity already exists in the fluid, however, it can be redistributed. Another way of thinking about this is that the wall is insulated from any vorticity flux. The bottom line here is that there's no vorticity production unless del omega del y at the wall is not zero. This is analogous to our heat flux case, where we had no heat flux unless del T del y at the wall was not zero. So in summary so far, our question from the previous lesson was for a barotropic fluid with conservative body forces, how is vorticity produced? The answer is that there must be viscous forces, there must be a wall, and there must be a vorticity gradient at the wall. We can have no vorticity production unless all three of these criteria are met.
Yeah, you keep giving us all these criteria, but you still haven't explained how vorticity gets into the fluid.
Yes, you're right, Professor Skeptic, but be patient. I'm getting there. To finally answer our question, we're going to have to look at the equations. Again, we're considering 2D steady incompressible Newtonian flow in the x1, x2 plane. I'm also going to ignore gravity for simplicity, and we'll assume that our wall is stationary. We start with the Navier-Stokes equation without the gravity term, which is written out here in tensor notation as equation 1. If you look back at some previous lessons, you'll see how we invoked two vector identities to get an alternate version of equation 1. In terms of vorticity, here the curl of velocity, which occurs in this term and this term. But we can simplify this further. The incompressible continuity equation is del uj del xj equals 0, so this term goes away. Right at the wall, uj is 0, so this term also goes away at the wall. Since we're talking about steady flow, this term also goes away. Now let's rearrange and multiply by rho over mu, which is the reciprocal of this. So equation 2 becomes this equation, which I'll call equation 3, and keep in mind that this is valid only at the wall. We can reduce this even further for 2D flow, where x1 is along the wall and x2 is normal to the wall, for example in a boundary layer. In this kind of a 2D flow, omega 3 is the only non-zero component of vorticity. And let's look at equation 3 for index I equal 1. In particular, let's consider this term. With I equal 1, we have epsilon 1jk del omega k del xj. But as we think about this term for 2D flow, only the k equal 3 components are non-zero. If you let k equal 1 or 2, this term goes to 0, since the vector omega is 0, 0, omega 3. Expanding this out with k equal 3, we have epsilon 1j3 del omega 3 del xj. Summing over j, we have epsilon 113 del omega 3 del x1, plus another term with j equal 2, plus a term with j equal 3. Well, remember that this guy is 0 and this guy is 0, and epsilon 1, 2, 3 is 1. So finally this term circled in blue reduces to del omega 3 del x2. Now consider this term. For I equal 1, we have del x1 of 1/2 uj. But since x1 lies along the wall, any occurrence of uj is 0, so this whole term is 0, and this term drops out. Our final equation then is del omega 3 del x2 is minus 1 over mu del p del x1 at the wall. And keep in mind that equation 4 is valid for 2D steady incompressible Newtonian flow with no gravity. As we discussed in our analogy, this term on the left is proportional to the vorticity flux at the wall, which is proportional to the production of vorticity at the wall. The term on the right is proportional to the pressure gradient along the wall, since x1 is defined here as along the wall, in other words, the streamwise direction. If you prefer to work in xyz coordinates, equation 4 can be written del omega z del y is minus 1 over mu del p del x. This is the notation we typically use when talking about boundary layers. So finally we have an answer to the question we've posed. How is vorticity produced at a wall? The answer is in a 2D steady incompressible Newtonian flow without gravity, vorticity is produced at a wall only when there is a pressure gradient along the wall. Here's an alternate expression. In a 2D steady incompressible Newtonian flow without gravity, a pressure gradient along the surface of the wall is necessary to sustain a flux of vorticity from the surface to the fluid. In other words, a pressure gradient is necessary for there to be vorticity production at the wall surface. In summary, for vorticity to be produced, we need viscous forces, a wall, a vorticity gradient at the wall, which from our equations we now know that we need a pressure gradient at the wall. If there's no pressure gradient at the wall, we cannot produce vorticity. In the next lessons, we'll look at how vorticity is produced along a 2D airfoil and for a flat plate boundary layer. Thank you for watching this video. Please subscribe to my YouTube channel for more videos.
That's all there is to it.